Hi, greetings from Finland to those waking up in California and the ones of you watching from the East Coast, to those in Europe around the corner, and the ones of you wearing pajamas and underclothes. So thank you for being here. And so today I want to talk about a topic that essentially is going to connect two big topics. One of them is going to be data analysis and more discrete flavor, and the other one is going to be something that is more analytical, geometric, and essentially my talk is going to be about connecting these two, and ultimately the connection is going to imply some new results, some high probability quantitative conversion rates for things that you do with data and how they compare to their ground truth limit. Okay, so then the first thing that I want to do is just like set up everything. So just a very basic kind of a description of the setup. So basically, we are interested in doing unsupervised learning. So we have a data set of data points. In this case, this images of very famous paintings, and then I just want to use maybe some geometric information about the relationship between these data points to find course structure in the data set. Okay, so that's the idea. And of course, well, that you could ask that question for data sets of famous paintings, or you could do unsupervised learning for data sets like the MNIST, where again, maybe what is important here is that you not only have the data sets as images or some sort of representation, but perhaps the important part is to have some similarity relationship between individual data points. This is going to be useful because it's what is going to give some sort of geometry on the data set. Okay, so now what is some of the things that you can do with this graph? Okay, so this graph, once you endow data sets with geometry, one of the things that you can do is define functionals that will help in the task of finding these clusters. Okay, so if, for example, in the case of MNIST, you have a graph that connects the data points in the way that is described in this picture. So then you could say, okay, if I want to give a notion of a cluster, then the graph allows you to do so. So it gives you like a concrete way of talking about clusters. So this idea of finding groups that have elements that are more similar or are very connected among themselves and not so much with points in other groups is made concrete when you have a graph. And in particular, you can introduce this objective function that basically measures how much interaction there is between a set of data points, a subset of data points, and other data points. Okay, so this graph cut functional is going to be like the center of today's talk. And for a graph is essentially defined in this way. You have a set AN, and then you're basically just counting how many interactions there are with the outside. Okay, so one thing that is just like a simple observation is that essentially that geometric notion, just counting or just measuring the size of an interface, you can write it in this a little bit more functional kind of way, which we will later talk about more. Okay, so of course then for the example that I had shown earlier, so if you have this, you take the subset to be this set over here, the one inside the blue bubble, then you can see, okay, so this group of 9 certainly is such that when you compute the cut of it, is basically saying that, well, there's a little interaction between that set and the rest, which at least matches the intuition that, well, this certainly is a group of 9s and therefore should be in one cluster. Now, of course, like one thing to keep in mind is that the cut functional on its own is not the best thing that one can do when you're trying to do clusters, because you can imagine that another set that has a small cut is, for example, a set consisting of a single data point, and although that set is going to have little interaction with the rest of the data set, is perhaps not the idea that we have of a cluster, namely because it's too small, it's too insignificant, so it's not a meaningful set. Okay, so then maybe under this consideration is that people later consider variations of this cut functional that we will talk in a second. But of course, maybe at this point, it's important to remark that this cut functional is everywhere. I would say it appears in computer science, in mathematics. You can think about this min cut max flow theorem. It's about cuts of graphs. But as I was saying, and perhaps for the purpose of the talk, more importantly, it is used for clustering. Okay, so maybe if we go to the one of the prototypical kind of functionals used for data clustering. So then we get to this Cheeger cut problem. Okay, so the Cheeger cut problem is this idea of saying, well, the cut functional is good because it's measuring interfaces. We want to have small interfaces that seems to be in alignment with the idea of clusters, but we don't want to have trivial or insignificant partitions. So maybe we should incorporate a penalization to partitions that have high asymmetry in terms of size. So at least if the intention is to cluster data into two groups, then this Cheeger cut problem is trying to mediate between trying to enforce small interaction between the two sets, but also by looking at this balance term, the denominator of this expression, you're trying to enforce the partition to be a little bit more symmetric, and in particular trying to rule out trivial partitions. Okay, so that's perhaps the standard two-way clustering scheme. And then the thing is that, unfortunately, at least in a generic graph setting, well, the computational complexity of trying to solve this minimization problem is NP hard. Okay, and so, well, in principle, that would be bad news. But at least one of the messages that I would like to give later in the talk is that, at least for some purposes, not so bad. It really matters what is the structure that this data set, that these data points have, these graphs have. Not all graphs are going to be as bad, and sometimes when you have a structure, then the discrete problem may inherit some properties. Okay, so I'll explain a little bit more what I mean later on as the talk evolves. Okay, but let's say just historically, the fact that this is an NP hard problem immediately motivates people to look for relaxations. Okay, so at least just as a historical kind of review, let me then talk about some of the relaxations that people have considered. So the most popular one perhaps is the one that goes as follows. So you say, well, we have our cut functional that, remember, I wrote it in this form earlier. And then you can say, well, for at least for indicator functions, you can square the difference between those two things, or not square it. At the end of the day, 1 square and 0 square is equal to 1 or 0. The same thing for -1. And then the idea is, well, you are relaxing the functional. So now, instead of just looking at functions that are indicator functions, now you look at functions that can take arbitrary real values. And then you replace the denominator of this Cheeger cut objective with something that is more like an L2 norm. And then you discover that this optimization problem is really just a characterization for the eigenvalues, eigenvectors of graph Laplacians. Okay, so basically the idea was, okay, so the graph, the Cheeger cut problem is nice. It has nice geometric interpretation, but maybe let's try to find relaxations that are much easier to compute. And so that leads us to this eigenvalue problem for the graph Laplacian. And this is perhaps the center of this spectral clustering algorithm that not only works for two-way partitions, but also for multi-way partitions, and you tend to use higher eigenvalues of the Laplacian. Okay, so this is more or less the idea that this NG et al. Paper has, and later in this tutorial by Ulrich von Luxburg, she describes pretty well. Okay, so now, of course, one can say, at that point, okay, there was like this interest in trying to find fast and good numerical methods, but of course there was also some theoretical motivation. Okay, so in particular, if you start putting a model on the data, so you start thinking like a statistician, or you say, okay, what if data comes from some distribution? And there were, I would say, two kind of lines of research. So one of them was studying models that would assume that these graphs, the ones that we were talking about, come from something more like a graphon or something like a stochastic log model. So it's a little bit less geometric, but a very concrete geometric, a very concrete model for how these graphs are generated. So how the data comes to be, essentially. And then there are other models that are more about, well, assuming that the data points are actually coming from some distribution on some ambient space, on some manifold. Okay, so you imagine that the data is supported on some manifold, and now the idea of a graph is induced by these data points by proximity. Okay, so then at least for the talk, I'm going to focus completely on the geometric kind of a model, where again, so the data points are assumed to be samples from some manifold in an RD, and we assume that the manifold is perhaps much lower dimensional than the ambient space. Okay, so now, of course, once you have the data, then I need to specify what are the weights, or what is the graph. And as I was saying, this is, in this case, in this family of models, these are induced by proximity. So basically, depending on the distance between the points and some length scale that essentially you specify to dictate what is close enough, then basically that gives you the graph. Okay, so here for a choice of epsilon and maybe some choice of kernel eta, in this case, this very, very simple 0-1 kernel, you would obtain a graph like that one. And of course, it's important to remark that this epsilon here, it's a parameter that a user chooses. Okay. So of course there is a big family of proximity graphs. So even in this geometric setting, you could have K-NN graphs, self-tuning graphs, graph based on higher order geometric structure. Each of these constructions will help you do data analysis for different purposes. Okay, so but at least for the talk, I'm going to focus completely on the epsilon graph, which is perhaps the simplest to analyze. And so, okay, but then just keep in mind that there are many potential constructions of interest. All right, so now what was one of the statistical questions that people were asking at the time? So we're talking, say, at the early 2000s and after that. So one of the questions was essentially one of the basic questions in the statistics: what happens with whatever you're doing, whatever estimation procedure you're doing, what happens as the number of data points grows to infinity? And here I'm going to put in parentheses also this desire to also send the connectivity of the graph to zero. So maybe this is from a computational motivation, thinking that the smaller the connectivity scale, well, the sparser the graph is, and hopefully this also means less computations. Okay, so then maybe this is just what any statistician would ask first, like what happens with whatever method you're doing now that we are assuming some probabilistic model, and this perhaps I would say that this is perhaps at the core of this idea of manifold learning. Essentially, if you can recover from data the underlying structure that basically generated the data. Okay, so so then maybe one kind of review of some of this literature. Manifold learning was originally very, very focused on the properties of the graph Laplacian. So maybe it's starting from this work by Belkin and Iyogi, which, as you can read from the title, is very, very specific and clear that the intention is really to connect whatever you do with the with your graph, with your data, and try to connect it with the continuum limit. What happens as n goes to infinity? And then after that, there were a bunch of, there has been a lot of work on trying to study asymptotic properties of these graph Laplacians. I kind of separated, I mean, there is a lot of literature. As you can see, I cannot fit everything in one slide, but basically there is one rationale on the way that I split this literature. At least the first four references here are mostly, okay, let's say the first three are mostly on pointwise consistency. I'll explain later what that means. But then maybe starting from the work of von Loxberg and Belkin, there has been analysis on spectral consistency. Okay, so this idea of spectral consistency is important because at the end of the day, the way that you are using this graph Laplacians is to either extract its a spectrum for clustering, or to do dimensionality reduction with the spectrum of the graph Laplacian. And so at least if you want to say that those methodologies that are based on extracting the spectrum of the graph Laplacian, if you want to say that those are consistent, if you want to describe how those methodologies behave, then of course what you have to do is study spectral properties of the graph Laplacian and not pointwise properties. So that's an important kind of observation at this point. Okay, but then if I've said that this has been kind of like the story for the graph Laplacian, the manifold learning mostly focus on the graph Laplacian, but I want to go back to the unrelaxed Cheeger cut problem, the original geometric problem, not the relaxation. Okay. So if we go back to our, at least for the graph that I showed you earlier, at least in my picture, my Cheeger cut problem looks like this one over here. Here, perhaps the one thing that I've done is change the cut functional and replace it by some rescale version of it. So basically, I'm calling this graph total variation. I'm defining it in this way. And well, basically what one can show is that essentially this is just a rescaling of the thing that I had shown you earlier that I called the cut. Okay, so I'm still solving just the cut functional, but I'm rescaling it appropriately because I'm later interested in taking limits as n goes to infinity and as epsilon goes to 0. In my picture, I'm also showing you a partition of what could be the solution to this Cheeger cut problem. Okay, so this is just kind of an illustration. All right, so consistency question. So now the manifold learning question, but now for the Cheeger problem. So what happens if the number of data points that we assume are sampled from some distribution supported on some manifold? What happens as we take more and more points and at the same time we scale the connectivity of the graph to 0? Okay, so you would expect, at least the picture suggests this, that in the limit, and at least if you take the limit on epsilon appropriately, in the limit you would like to see that this discrete Cheeger cut is converging to some sort of partitioning in the continuum limit that hopefully is also a minimizer for something reasonable, but now at the continuum level. Okay. So if one wanted to make a kind of mathematical sense of that observation, of that guess, then well, what would be the challenges to kind of establish a result of that type? In other words, how can we characterize the large sample limit of this Cheeger cuts? Well, so the thing is that traditionally in this kind of statistical problems, well, here we're facing a nonlinear, non-convex, random variational problem. Of course, we don't have an explicit solution for what is the minimizer of this functional, and so this already makes the problem difficult to analyze. The second observation is that here one is looking over all possible subsets of the data set. Okay, so here I'm not restricting a priori on a specific class of subsets of X, but rather I'm considering all possible partitions. Okay, so these are two things that make this problem difficult from the traditional point of view of, for example, a statistical learning theory. Okay, so and here, especially, let me talk a little bit first about the second point, the optimization over all subsets, and this relationship with the statistical learning theory. So there was a paper of Farias Castro et al. In 2011, around that time, where this same problem, this Cheeger problem, is kind of replaced a little bit. And instead of considering all possible subsets of the data set, what they do in their paper is consider subsets that are obtained by restricting to the data set nice subsets on the manifold. Okay, so imagine for a moment that you have knowledge of what the manifold is, and then imagine that you have a collection of nice subsets. By nice, I perhaps mean sets with a regular enough boundary. And so then I consider my allowed discrete subsets to be restrictions of those nice subsets on the manifold, but now to the data set. And well, what happens when you do something like that is that now from a statistical point of view, the analysis now becomes a little bit easier, because now you can say, well, now I have a family of objects that perhaps have a small dimension. Here I'm talking about something like VC dimension or capacity measures, but essentially that puts you in the framework of a statistical learning to analyze some of this. Okay, so maybe what I mean by that is the following. So what is the classical approach from a statistical learning? So you're trying to estimate uniformly an empirical functional. So this epsilon n is something that depends on data. This capital F is some class of functions. And this capital E here is perhaps some asymptotic, some population level objective function. And so the idea is to try to estimate uniformly the difference between the empirical quantity and the ground truth. And the way one can do that is, well, if the class of functions F is not too large, essentially what you end up doing is some sort of concentration inequality and some smart usage of union bound. So in the case of the paper of Farias Castro et al., the way this would work more or less is by saying, well, my class of functions are some indicator functions. Indicator functions of what? Well, those are nice subsets of the manifold. And well, what is this empirical or data functional? Well, it's just the Cheeger cut. Well, not the Cheeger functional. And what is this E? Well, it's going to be some sort of population level objective that in this case it looks like this, which is essentially like a large data limit of the graph total variation. Okay, so when you take n to infinity formally, you would expect to see an object like this. Okay, so this is more or less the framework, the statistical learning framework in that paper of Farias Castro. But once again, the observation is that the class of functions is restricted to nice enough subsets of M. From a statistical point of view, nice, I don't see a problem with this, but from a practical point of view, this is not so good in the sense that there is no way to guarantee that your partitions are going to be nice enough subsets of M. A priori, we don't have that information, and there is no way to enforce that constraint because, of course, in most of our applications, we don't know what the manifold M is. Okay, so then that's maybe why we don't, I mean, we are trying still to understand the problem in the unconstrained setting. So we're not enforcing regularity a priori. And so if we want to analyze the true Cheeger cut problem, the one that is unconstrained, this approach cannot work, the one that I just described, because the class of functions is the entire set of partitions. So that's a very, very large variable. It's as large as it can be. So we cannot really use the same approach. Okay, so here, if we want to do some progress, we have to come up with some idea so that we can put the probabilistic estimates where they're not going to kill us, and essentially we can extract some sort of convergence rates to relate these problems. Okay, so now what I want to tell you is a first approach to this problem. Okay, so trying to connect the discrete problem with something asymptotic in the limit, and we're trying to connect in whatever way we want. So first, I'm going to give you a series of results without rates of convergence, and then we will later enter into the actual topic of the talk, which will be to talk about these rates of convergence and the relationship between the Cheeger problem and the isoperimetric inequalities that I announced at the beginning of the talk. Okay, so at least for now, then, this what I'm going to discuss is based on these two papers, one of them in a machine learning journal, another one in an analysis journal. Again, this is more or less the way I operate, trying to bring connections between discrete and continuum. All right, so asymptotic consistency. Okay, so here, not interested in rates of convergence. I just want to know how should the connectivity of this graph scale with the number of points to guarantee that almost surely the Cheeger constant on the graph converges to some analog Cheeger constant in the limit, and that minimizers of the Cheeger problem at the graph level converge to some minimizers of some object at the continuum level. Okay, so then in this case, I'm basically telling you that if the connectivity of the graph doesn't go to zero too fast, so it goes to zero but not too fast, then indeed with probability 1, what we did in the works that I showed you earlier is precisely to show that we can recover the Cheeger constant of the manifold in the limit, where now what is the problem that we're considering the limit? This one over here. So it's like a TV, the total variation or perimeter, and we have a similar balancing term where mu is the measure that we use to sample the data. Okay, so not only the constants converge, so the minimum values of this problem, but also the minimizers of the discrete Cheeger problem are expected to converge to the minimizers of this limiting continuum problem. Okay, so for those of you who maybe are not super familiar with this TV functional over here, so I have here this one slide. So if one has to be a bit rigorous, so then this TV is defined via duality in this way. But at least for you to, maybe if you're not familiar with this, at least to have something in mind, this TV is essentially a perimeter, at least for a smooth sets, so sets with a smooth boundary. What you end up doing is just looking at the surface integral, just measuring how big is the interface of a set A. Okay, so then just to recap, then what I'm saying is, with probability 1, as epsilon goes to 0 no faster than this rate, then the discrete Cheeger problem converges to a continuum Cheeger problem. That means that the Cheeger constants converge, but also that the associated Cheeger cuts converge. Okay, so that's something that we did a few years ago with my advisor Dan Sepchuk, who's there, and hi, and also with James Mombrecht and Thomas Laurent and Xavier Besson, UCLA represented. And so one thing that is important to observe in these results and in these proofs is that they use tools that essentially don't allow us to see right away that there are rates of convergence. So we don't know how fast this convergence is happening, and well, even less for the things that are happening here. So we don't have that. There's one more remark that I should make, is that I think 2 years ago, in a work by Penrose and Mueller, they improved this lower bound here in the case n is equal to 2. So instead of being 3/4, the answer should be 1/2. And Penrose and Mueller in their work, they're able to improve the lower bound in this condition over here. Okay, so but okay, at least for the storyline of today's talk, the important thing is that this proofs didn't give us any rates of convergence. Okay, so now for the rest of the talk, I want to tell you about the rates of convergence. And I'm going to do it in 2 steps. So the first one is going to be about Cheeger constants, so just the minimum values. And then in the second step, I will talk to you about the Cheeger cuts, so the minimizers. Okay, so let's start with the Cheeger constants. So the first thing is, if we wanted to relate those Cheeger constants, then we can do it in further two steps. So in the first step, we can try to do an upper bound, so namely trying to, for the discrete problem, try to say that asymptotically is smaller than the Cheeger constant plus maybe some error, Cheeger constant in the continuum. And in reality, this is the easy bound. So this upper bound is the easy one. By easy, what I mean is that we don't really need any exotic tool. We just need a basic concentration inequality. And so the idea is to say, well, if we wanted to obtain this upper bound, what we can do is the following. We can say, well, let's just fix a solution to the Cheeger problem at the continuum level. So this is this A star that I have here. And then for that specific function, we use a concentration inequality that will allow us to relate the graph total variation with this non-local TV that I showed a couple of slides ago. So it's basically what would be the expectation of this graph total variation. Okay, so for that specific function, one can use this concentration inequality, and one can get pretty good bounds of how close this random variable is from its expectation. And then we can use basically a little bit of analysis and say, well, essentially when I do the total variation of that minimizer, that's going to be greater than this non-local total variation. So that's a little bit of analysis that essentially says that this local quantities kind of upper bound than non-local ones. And then I apply essentially just a basic subtract and add back the same thing, and use the concentration inequality to say that basically this quantity over here plus some error is below the TV for that specific set A star, which is a solution to the problem. So then from there, of course, essentially the result is going to follow the upper bound, because essentially what you do is, well, we have this graph TV is less than this guy over here plus some error. Then again, you can use another concentration inequality to say that, well, essentially the volumes, the discrete volume and the continuum volumes are also going to be very close to each other. We're doing everything for a fixed set. And then you just put everything together. You realize that, well, you picked a solution to the continuum problem. So that quotient gives you exactly the Cheeger constant in the continuum. And then you use these approximations to go down and then basically say, well, here I'm looking at a particular set. Definitely this quotient is going to be greater than the minimum value of that quotient, and that gives you the upper bound. Okay, so that's more or less the idea. So that's always the easy bound. But for the lower bound, things are a little bit more delicate. For the lower bound, you really need to do a smart or a clever control of what can go wrong for all possible sets, essentially. Okay, so this is a proposition that is going to be important for establishing the lower bound, and later when I talk about the Cheeger cuts. And so basically what we prove with Ryan Murray and Matt Thorpe is the following. So basically we can construct this essentially an interpolation map that relates to every possible discrete subset of the data set. So for every possible subset of the data set, we can associate a subset on the manifold. So, okay, so this is my interpolation map. And this interpolated set, if you like, has the following properties. So the first one is basically saying that the interpolation is not too far away from the original set. So we're saying basically, so we're saying essentially that the difference between the original set and its interpolation is going to be bounded by something that is small. I mean, depends on the size of the boundary of the original set, fine. But essentially, morally speaking, is going to be the right-hand side is small. So we're saying the interpolation and the original set are close to each other, first thing. And then the second thing is that, well, that we can control the perimeter of the interpolated set with the perimeter of the original set. Okay, so and this is perhaps the main property we're interested in, because essentially what is going to imply is that now that we have this whole these conditions for all possible subsets of the data set, now we can essentially do the same trick that we did for the for the upper bound, but now for the lower bound. So namely, we would start with the solution to the discrete problem, and then we would interpolate, and then we would reduce the energy in this way to obtain a lower bound over here. So okay, so then just to recap, what I'm saying is that this is more delicate because we need this sort of inequalities for all possible subsets of a data set. But what I'm saying is that this is, once you have a result like this, then you can obtain the lower bound for the Cheeger constants in a more or less simple way. Okay, so then let me tell you what are the key ingredients to obtain these properties over here. So I would say that when analyzing this discrete to continuum problems, when the discrete depends on random data, there is one key ingredient that appears in pretty much every proof that I've seen. This is the case for this thing that I'm presenting to you here, but it's also the case in some of the work of, for example, Jeff Calder on analyzing other types of graph PDEs. It's always about finding the right interpolation, and it's always about proving or energy estimates or properties of that interpolation. Okay, so it's always a little bit about that. So here is no exception. But now, so what I want to tell you is a little bit of just deterministic inequalities. So there's nothing random here in what I'm showing. This is just relationships that hold for the deterministic problems. So there's nothing random, and I don't expect you to look carefully at these things. I'm just saying nothing here is random. But the point is that what basically these inequalities are doing is relating the total variation, the actual local total variation, with these intermediate objects, these non-local total variations. Okay, so there are some properties about what dominates what, so namely if the total variation dominates the non-local one, or what happens when you change the scale of these non-local operators. What is the effect of regularization? So, for example, here, etc., etc. Okay, so there is a bunch of inequalities that one can use before introducing any randomness in the problem. And so then with all those properties, one can get estimates or properties like this, that basically for all functions, basically, what you have is if you do a convolution of a function and then you compare with the original function, then the difference between those two things is going to be controlled essentially by the size that you use to convolve, and also by the in this case the non-local perimeter for f, or the non-local total variation for f. So this should resemble a little bit the first property that I listed earlier for that my interpolation had, but then also some property related to, well, you can start with the total variation, and then by applying something, you can reduce the energy, which again sounds a lot like what we wanted earlier. Okay, so, but once again, this is something that one can do completely deterministic. There is nothing probabilistic at this point. And then if what one can show is that essentially everything, all the properties that I wanted for my random discrete problem and relating them to the continuum problem essentially boils down to understanding what happens between this graph total variation and this non-local total variation over here. So if one can basically, with this guy, upper bound this other guy over here, then essentially one can use this deterministic inequalities, and one essentially obtains the desired properties. Okay, so this is more or less the idea. And just to give you a flavor of the way this is done, is as follows. So basically, if we have a discrete set, we're trying to build this continuum set. What we do is basically composing that discrete set with a map that takes you from points on the manifold into the data set. This map has certain properties. So in particular, it preserves the mass. So it relates the ground truth measure with the empirical measure, and we want it to be such that it doesn't shuffle points too much. So if you have a discrete subsets of data points, for example, x3, x5, and x6, this composition essentially is going to give you the union of the regions U3, U5, and U6. Okay, so to every discrete set, there would be some analog continuum set. Then you can do. Then what you can see is that there is a almost deterministic relationship between those the graph TV of the original set and this non-local TV for this set that I constructed by composition of these maps. And then what we do is say, well, if this thing if this term over here I can make it small, then what we basically will be the relationship between this graph TV and this TV epsilon that I wanted to do. Okay, so basically here is where the probabilistic estimates come for the very first time. Essentially, they're essentially used to try to bound this thing and to make it as small as possible. That's going to put some restrictions on epsilon, but essentially it's going to say that this graph TV dominates the TV up to some error term. Okay, so one puts together this with the other deterministic estimates, and what one obtains is a result that reads more or less like this. So basically, this is the first result that we present. So it says that as long as the epsilon doesn't decay too fast to zero, with very high probability that you can quantify, you can write exactly the exponential decay. Essentially, the difference between these Cheeger constants scales in this way. And it gives explicit dependence on the connectivity of the graph and the number of data points that you have. Okay, so one quick observation: do not expect this to be optimal. It is not optimal, but these are the first type of estimates that are out there. Okay, so this is not optimal, but is concrete convergence, high probability convergence rates of the Cheeger constants from the graph to the map. Okay. All right, so this somehow puts an end to the first part of the discussion. So that was what happens with the constants, with the minimum. But now I really want to talk about the convergence of the minimizers. And I really want to talk about this because, once again, if we go back to one of the reasons why we didn't like the Cheeger cuts was because we thought, okay, this is NP-hard, so no reason to analyze it, maybe there's no point here or hope. But of course, and this is not an observation that I'm making. I mean, this observation has been made several times in the past, that the fact that a problem is NP-hard doesn't mean that for all the problems that we care about, or for problems where we have some sort of a structure, the things are going to behave as bad as the worst case scenario. Okay, so here, from the statistical point of view, I'm not going to talk about the optimization point of view, but from the statistical point of view, what I want to show you is that analyzing the minimizers, so the convergence of the minimizers, is possible thanks to very deep and very interesting mathematics. Okay, so this is really why I want to talk about this. So okay, so now one of the things that what I'm going to discuss now does for us is going to make explicit some sort of right notion of convexity or local convexity that is not explicit in the problem, but we will be able to see it, or at least some very smart mathematicians will allow us to see. Okay, so let me then talk about convergence of minimizers. And in order to do that, I want to take a little detour into isoperimetric inequalities. Okay, so maybe you've seen this problem before. I think this is a very famous and very classical problem. In dimension 2, imagine find a closed plane curve of a given perimeter that encloses the greatest area. I hope that we all know that the answer is the circle. And of course, this is a problem that is very classical, with a very rich history, perhaps goes as far back as the Greeks, maybe even earlier. And then maybe more modern treatment with more mathematics, from Steiner, Benand, Riley, and Poincaré, all these very important people, and into the 20th century, early as Poincaré, and the 30s and 40s with Segman Polya. And interestingly enough, the history continues. I mean, to this day, probably I would have to put more names, and I will do that in a moment. The list is much longer, but then let's just say one basic mathematical way of writing the yes.
I have 1 minute.
Oh, I have 1 minute.
Five.
Oh, 5. Okay, sorry. Okay, so then basically what we're trying to do here is saying, well, the problem is if you fix the volume of a set, you're trying to minimize its perimeter. So this is equivalent to trying to fix the perimeter and maximizing the area. And then, well, the isoperimetric inequality is basically going to say that the answer to that question, what is the minimizer, is the circle. Okay, and so this is manifested in this inequality here, the isoperimetric inequality. Again, the isoperimetric inequality is a very important notion. But now I ask the following question: what about a quantitative version? Okay, so we know that the best possible set is the circle, but what if we had a set that is close in perimeter to the one of the minimizer? Okay, so then in particular, suppose that you have a set E whose volume is V and whose value of perimeter is very close, is delta close to the minimum value for the perimeter for a set of volume B. Okay, so then can we say, knowing that the perimeter is closed, do we have some quantitative rigidity property that is going to tell us that this set is close to being a ball or close to being a minimizer? Well, so this question goes as far back as Bernstein, and it has received a lot of attention during the 20th century. But perhaps the kind of like the climax of this was in 2008, when Fusco, Maggi, and Protelli gave a concrete proof of an optimal sharp dependence on the perimeter deficit, so namely how far you are from being a minimizer, and in terms of perimeter, and how far you are from being a minimizer in terms of the difference between these two sets. As you know, like how big is the symmetric difference? How can we control that symmetric difference with the difference of perimeter? So in this work of Fusco, Maggi, and Protelli, they were able to show that the dependence of the difference on perimeter and how different these sets are is like this, with the power 2 over here. After that, there was a paper by Figali, Maggi, and Protelli, who also considered the same problem, but now using different ideas and maybe generalizing to anisotropic perimeters and so on. Okay, but now one of the things that this proof of Fusco, Maggi, and Protelli, one of the things that they don't do is, well, they use arguments that are somehow unique to Rn. Okay, so they rely on symmetrization arguments. And so you cannot really see this notion of convexity, something that perhaps could apply for more general settings like manifolds. Manifolds like the ones that I'm thinking about are the ones supporting the data. So then, fortunately, there was a second proof, or the third proof of this quantitative isoperimetric inequality by Cicalesi and Leonardi, who indeed do exhibit such a construction. Okay, so their proof reveals that there's some sort of right notion of convexity that perhaps is easier to understand. Okay, so and one of the things that their proof does also is that it allows for extensions to manifolds, and so this is indeed something that was done very recently, just last year. And then basically, Chodos, Schengelstein, and Spoller, what they do is basically show this a similar isoperimetric inequality for manifolds, but now assuming some properties on this solution to this to this mass constraint perimeter minimization problem. So basically, if you have smooth boundary of this solution of the boundary of the solution, and you satisfy one of two properties. So either this thing is a strict or integrable, and I'll say that what that is in a moment with a picture. But under those conditions, you essentially recover that relationship between the difference of perimeter gives you control on being close as sets. So something being close to a minimizer. Integrable and strict in pictures. So the one on the left is integrable because you can do like you can translate and you stay within the set of minimizers. The one on the right is strict because it has what I was trying to get to, which is this right notion of convexity. Okay, so this right notion of convexity is basically saying that if you look at the formations of the solution, and if you look at the second variation of the formations of the solution, essentially you have a strong convexity around that minimizer, which is characterized in this way. Okay, so then basically this is the characterization of a strict minimizer. But the point is that with those notions, now we can put together what we had for the Cheeger cuts, like the Cheeger constants, namely perimeters. So we have some understanding of what happens between the difference of the discrete problem at the level of energy that it reaches, and we know that it's close to the level of energy of the continuum. But now these isoperimetric problems, these quantitative isoperimetric inequalities, what they give to us is being able to transfer difference of perimeter into difference of sets. Okay, so then our theorem with Ryan and Matthew, what basically says is that if we are in this situation of generic manifold where we have this integrability or a strict minimizers, then we can show that the solution to the discrete Cheeger cut problem, the Cheeger cuts, do converge to the to a continuum Cheeger cut, and we can quantify the rate at which it does so. Okay, so one observation, and I think time is running out for me.
Yeah, you passed the time. Like,
all right, so just
wrap it up.
Right. Okay. So then, basically, in our proof, there is some extra factors that it comes from the fact that we're using volume constraint and not Cheeger energy directly. We believe that definitely this 1/8 should be really 1/2. So we have some ideas on how to do that. But again, the point is these are concrete quantitative rates that somehow suggest that although the Cheeger problem is in principle NP-hard and from a statistical point of view may be difficult to analyze, well, if we are in a situation where we have a structure, in particular when we are in a geometric setting, then the analysis comes to our savior and actually gives us more structure than perhaps we could anticipate it. And the results that I presented are a proof of that. Okay, so one thing that is interesting is not just the statistical properties, but also the optimization properties. But of course, that will be for a later time. All right, so if you're more interested in this, then, well, just stay around after I finish and we can talk more, or just check the preprint paper that is on the archive. And with that, well, thank you so much for your attention.